This is Computer Architecture CS147 of San Jose State University. This lecture 7. Last lecture, in lecture 6, we discussed about the combinational logic gates and also combinational logic circuit design step. Uh, Now this lecture and part of next lecture will be talking about sequential logic, which is very important in modern computing systems. Uh, in fact, without these sequential logic and corresponding elements, it won't be possible to actually construct any computing system. Okay, so this is very important part of modern and all the computing system that you can think of. So our topic, what we'll do, we'll try to understand what is the concept of the sequential logic circuit and sequential logic operations, and then we'll go and do the storage element discussion. Once we understand the sequential logic circuit and its how it operates, we'll see that there needs to be a storage element like which can store information. Okay, which can store information either indefinitely or like within the operation time of that circuit, mainly power on power off time. During that time something needs to be stored as to proceed to the next step. So this is very important element and element of computing system, without which we won't have any computer. Okay, so sequential logic circuit, let's discuss the concept of it. Combinational logic circuit, as we have seen in the last lecture, lecture 6, you can think of it as kind of forward logic propagation circuit. Means we have like certain set of inputs, incoming, right, and we are we are just placing those inputs onto this circuit, and through various stages those logic gets combined with one another. It transform, translate, and so on and so forth, and but at the end of the day it becomes an output by combining logic values of those primary input. Right, here in this example, like primary inputs are x, y, z, and this function realizes a boolean function f of x, y, z, which is the output, primary output, and inside that it will have like stages of logic transformation and translation. For example, the last lecture circuit, right, we came up with some circuit like this, right? So we have this primary input a, b, c, d, and we have primary output w, x, y, z. So we can see clearly there is like stage 1 transformation of combining these independent boolean variables or the primary input of the circuit, right? This is stage 1. So first stage is like all the inputs of these corresponding logic gates, if you see, they are all coming from primary inputs. That is stage 1. And then there is stage 2, where you can see it's primary, these set of gates, this red set, these gates inputs are coming either from the output of stage 1 or from primary input. Okay, so every stage can have a primary input, that's fine, but point is that what stage I will make it, like that would be like what is the highest stage from which it's one of its input is coming. So that's going to be my stage number for this stage as well, like +1, of course. So this is for this set of gates, the highest number, like highest stage number from which its input is coming is 1. So this red stage, this gate set of gate has stage 2. Okay, then similarly we can see there can be a stage 3, where the inputs is either coming from the primary input or from stage 1 or from stage 2. Okay, so that becomes stage 3. So in this example, I think, yeah, we have this gate is driven by stage 2. Is there anything that driven by stage 1? Yeah, this input is driven by stage 1, and this input is driven by stage A, right? These circuits, these logic gates. So this is my stage 3, and we have stage 4 as well, one single gate whose input is coming from either primary input or stage 1 or stage 2 or stage 3. For this specific example, this blue one, or primary inputs are coming from stage 3 and stage 2, right? Stage 3 and stage 2. But nonetheless, after that it becomes, these are your primary output, right? So your logic from the primary inputs are getting combined, translated, transformed through stages of logic circuits, like logic combination. It is always kind of forward propagating logic combination. So that's what we mean by forward logic propagation circuit. Now, for the sequential circuit, this logic actually can go forward, and also this combination can come backward. What is meant by the backward essentially means your current output of any stage as well as your primary output can be depending on a previous computation result. Okay, can be dependent on previous computation result. So you can think of like, I started that circuit, okay, and I start the circuit and enter certain logic input, like that is, let's say this is for time point 0 or time point 1. So first time we turn on and give an XYZ input to the combinational part of the circuit. Now this combinational circuit, not only takes this primary input, one or more component can be coming from a previous computation. Let's say we are computing at a time point T10, okay, or iteration 10. Iteration 10's primary input can be some combination, and another set of input comes from as an artifact of iteration 9. Okay, so that's what it's shown here as an example. Let's say I am going for a computation iteration of 10, which is like my function is going to be t plus 1, which is like, let's say that is 10. And this combinational circuit also can spit out something like another Boolean function output gt plus n, g10 in this case. That g10 gets stored in the storage element to be used in computation for 11th iteration. Okay, while for the 10th iteration, it is not only XYZ but also GT, some artifact of 9th iteration at 10th step. Okay, 9th iteration at 10th, result of 9th iteration at the stage of the 10th iteration. So that's what the GT is. So for F10, okay, you will be using G9 and XYZ at that moment, whatever the logic combination is there. At F5, we'll use FG4 into this combinational circuit, and whatever the logic combination at that point of time. Okay, so that's the whole concept, and we'll store this some part, or maybe sometimes your GT plus 1 is equal to FT plus 1. We store everything. Sometimes it can happen, but in general, it is this whole function or some partial result gets stored from that iteration step. So mathematically, it expressed as this: that function of t plus 1, it means my next iteration, t plus 1 signifies my next iteration, is some function of XYZ, and GT means partial result from the previous iteration, where we also define g function gt. Gt is gt plus 1, means g at this at next iteration is going to be another Boolean function f2, which depends on xyz and gt. Okay, the partial result of from this iteration. So t is the number of iteration, you can say. So now this problem, actually you can think of, if you just walk back from iteration 10, which depends on iteration 9, iteration 9 depends on iteration 8, and so on and so forth. How about iteration 1? Okay, when you power up the circuit, okay, that is f1, very first time it's trying to compute something out of this combinational circuit, which need to have xyz as a primary input. That's not a problem. What is my z0? What is my g0? That's the question. Because we power up this circuit at f1, right? That is the very first iteration we are making. What is my g0? What can be the value of some step which I never did, right? This is the first time f1 I'm computing something. G1 is also coming up on that, but I need to have something like a g0. That thing is called an initial condition in a sequential logic circuit. Every sequential circuit has a power up state. What is a state? State is a value stored in a storage elements at one time point, at any time point. Okay, at any time point, the value stored inside the storage element. That's called a state. An initial state is that set of logics stored in the storage element when you power up this circuit. Okay, that's my G0. That's my initial condition. So when we power up, this storage element needs to be at a predefined combination of binaries. Depending on circuit, it can vary. Usually it is all 0, usually, but it can vary again. So that's my G0 in a sequential circuit. All right. So there can be two types of sequential logic circuit. One is definitely the one we just presented here, like it is an unrestricted feedback, you can say, from iteration 11 into the next and next and next. You can iteration 11 to iteration 12, iteration 12 to iteration 13, and so on and so forth. So essentially what will happen if you think, if it is an unrestricted feedback, like, okay, I at f10, like 10th iteration, I am evaluating a logic value f10, that's fine, and also I am doing a g10, this computation, and this g10, if it goes and kind of hand over at this output port, remember these are all electronic circuit, right? So whatever coming into the circuit, it will reflect something at the output if we don't restrict anything. Like if you think of, like, this is also a, let's say, some sort of combinational circuit, you can see that if this is also a combinational circuit, we just, this guy will translate into something and almost immediately appear at this part, right? So, and that getting feedback into my computation, and that will change or may change my f10, right, at this point. So this is kind of a very tricky situation here to what to store and when to hand over these. And with usually, if we think of this part as another combinational circuit, it's very hard to control that circuit because of this type of feedback through the combinational circuit over and over again, and your output can become very much unstable. But people design it sometimes. It is called an asynchronous circuit, and because it can make a sequential logic circuit very fast, very fast evaluation result can come up in this type of circuit. but very hard to design. So we don't find much of asynchronous circuit in the real computing system. So I believe some years back, AMD claimed that they have actually designed and successfully produced an asynchronous processor, but that kind of I would say yet to verify that it's not a full true claim. It's not a fully true claim in that sense. Okay, I believe that's more like a marketing gimmick and so on and so forth. But we need to verify that. Okay, just don't take my word as granted and assume that it is not possible. Maybe, but it is not that much popular. It is not in the market. Nobody else talks about it. So that's my reason to infer that was kind of a marketing gimmick. It's not really an truly asynchronous processor as such. Now, what is more common in all computer, and all computer uses the type of circuit which is called a synchronous circuit. So these kind of storage element also have a specific input for clocks. So you remember the clock, and clock is kind of a reference for giving time notion to rest of the circuit. So that is used as a stopgap between when my current iteration value, feedback value, will hand it over to for the next iteration. Okay, so that's kind of control that whole things. Like, let's say iteration 10, we are picking up iteration 9's partial result, combining them, result into F10, partial result G10 came in, but it is not immediately handover. It is stored in the storage element, but at the next clock cycle, it usually at the next clock cycle, depending on the circuit, it can be like 2 clock cycle or 3 clock cycle afterward. That is immaterial, but not at this moment. Not at this moment, just G10 gets handover to the output of the storage element, so that it may kind of contaminate the F10 result. It holds on to that, and for the next iteration, F11, which happens on the next clock edge, okay, at that point it hands over G10 value for the F11 computation. So it is kind of get synchronized with each other with respect to the feedback value and the incoming input values. This is the circuit is used for every computing system, every digital computing system. Okay.